Hello and welcome to yet another video of Cornerstones of Math. Today we are going to solve the geometry problem, but I think just solving the geometry problem makes this video, well, too short. Therefore, I also added the limit problem, where we are going to use our limit knowledge to think about limiting cases. Now that sounds pretty fun, but first let's take a look at the geometry part of the problem. In the following trapezoid with A and B as bases, where A is the longer base and H as the height, the line segment in the middle, that is, this line segment, apart by distance x from the long base, divide the trapezoid into two equal areas. And we have to find x and express it in terms of given length AB and H. Alright, let's solve this problem. Obviously, we have to formulate the equation using the given area condition, but in order to express the areas of top and bottom trapezoids, we need to find this length C. And in order to find C, we have to do this. Connect these two vertices by drawing a diagonal, and we try to find these two lengths M and N. And we can find M and N using the similarity of triangles. First, from the similarity of these two triangles, the ratio between M and A is equal to the ratio between the heights of the triangles, which is h minus x to h. Next, from the similarity of these two triangles, the ratio N to B is also equal to the ratio between heights, which is now x to h. So we have M equals h minus x over h times A, and N equals x over h times B. Therefore, length C, which is equal to M plus N, is given as A times h minus x plus bx divided by h. And now it's time to use the given area relation. But here, instead of using the condition that area 1 is equal to area 2, let us formulate the equation by using alternate expression of this condition, which is that the area 1, the area of the bottom trapezoid, is 1/2 of the area of the whole entire trapezoid, which is the combined areas of area 1 and area 2. The advantage of using this relation becomes clear if we actually set up the equation. The area of the bottom trapezoid is given as 1/2 times the sum of two bases A plus C times the height x. This equals 1/2 of the area of the whole trapezoid, which is given as 1/2 times. Now the two bases are A and B, so we have A plus B, and the height is h. Therefore, there are no x on the right-hand side. X is only on the left-hand side. If we multiply 4 on both sides, we have 2a plus c x equals a plus b h. Now x is only on the left-hand side, but it is actually not as simple as it looks, because this c also contains x for its expression. So using this expression for c, the equation becomes 2 times a plus a h minus x plus bx divided by h times x equals a plus b h. So we have to find x from here, and let's first multiply h to remove the fraction on the left hand side. Then we have, let's write 2x first, then ah plus a h minus x plus bx here, and this equals a plus b h squared. Now notice that the inner part of the parenthesis gives 2ah minus ax plus bx, so this equals a plus b h squared. And if we expand, we have 4ahx minus 2ax squared plus 2bx squared equals a plus b h squared. Here, let's move everything to the right-hand side. Then we obtain 2 times a minus bx squared minus 4ahx plus a plus b h squared equals 0. Here it is stated in the problem that a is greater than b. Therefore, this leading coefficient 2 times a minus b is positive, which implies non-zero. Therefore, this is a quadratic equation. So we use the quadratic formula, which gives x equals 4ah plus minus square root of 16a squared h squared minus 8 times a minus b, then a plus b h squared, divided by 4 times a minus b. Here we can divide both numerator and denominator with 2, which gives 2ah plus minus square root of, and because of the radical, the inner part must be divided by 4, which gives 4a squared h squared minus 2a minus b, a plus b h squared, divided by 2a minus b. Here, this a minus b times a plus b gives a squared minus b squared here. And if we simplify this inner part, we obtain 2a squared plus b squared h squared. So because of this h and this h squared inside the radical, we can take h out of the fraction. Then we have 2a plus minus square root of 2a squared plus b squared divided by 2a minus b. So we have obtained this, but we still have to deal with this plus minus sign. Let's consider the plus sign first. If we take the plus sign, it gives x equals 2a plus square root of 2a squared plus b squared divided by 2a minus b times h. Here, this a squared plus b squared is greater than b squared plus b squared. And notice that this part simplifies to just 2b. So we have 2a plus b divided by 2a minus b h, which is clearly greater than h. So it gives x that is greater than h, which is invalid. Therefore, we have to take the minus sign, which finally gives the correct answer, x equals 2a minus square root of 2a squared plus b squared divided by 2a minus b times h. Now, like I said, I am going to handle some limiting cases. Specifically, I will address the question, in your obtained answer for x, which is this, what happens at the limit, first when b approaches 0, second when a goes infinity, and finally when a approaches b. So let's address these cases. First, when b approaches 0. Then we have the limit of x as b approaches 0, which is this limit, and we can evaluate this limit by simply letting b as 0 in the given expression. This gives 2a minus square root of 2, then a can come outside, divided by 2a times h, so a can be cancelled out, and we have 1 minus square root of 2 over 2 times h. Now some of you might find this expression rather familiar, and perhaps even understand why it looks so familiar. This is equivalent to triangle case. And when it comes to triangle, the problem is simpler. If the green area is half the area of the entire triangle, then you can easily notice that this length is square root of 2 over 2h, making this x equal to 1 minus square root of 2 over 2h. Next, when a approaches infinity. Here, the expression is the same except this a goes to infinity. And this is the infinity over infinity type limit, with the numerator and denominator having the same degree for a. So we only take coefficients of the highest degree terms, and in the numerator, we have linear term 2a here, and also the linear term square root of 2a from this radical. And in the denominator, we have the linear term 2a. So we have 2 minus square root of 2 over 2 times h, which is equal to 1 minus square root of 2 over 2 times h. Here you can notice that the answer is the same as the previous case, which was the triangle case. That is, a becoming infinitely large while b remaining finite is equivalent to the triangle case. And finally, when a approaches b. Here, if you inspect the limit, you can notice that both numerator and denominator approach 0 when a approaches b. That is, this is 0 over 0 type limit. Therefore, in order to evaluate this limit, we multiply 2a plus square root of 2a squared plus b squared on both numerator and denominator. Then, applying this formula, the numerator becomes 4a squared minus 2a squared plus b squared. And if we further simplify the numerator simplifies to 2a squared minus b squared. So we can cancel out 2, and more importantly, we can cancel out a minus b in the denominator, and this leaves a plus b in the numerator. So we have the limit a plus b divided by 2a plus square root of 2a squared plus b squared h. And now we can finally substitute a with b, which gives 2b divided by 2b plus, and the square root part also gives 2b, so this times h, which gives h over 2. And of course, this is the same value as expected from the rectangle case, where these lengths are both h over 2. And that's all for today's video. Thank you for watching. Please hit that like and subscribe buttons if you enjoyed this video. And as always, I will see you in another video.